So, Alan, it's all yours.
Okay. Yeah, so it's a real pleasure to present Ken Meyer's talk, in particular because Ken doesn't need any presentation. Everybody knows his works on Hamiltonian systems, on periodic orbits, and their bifurcation, stability, normal forms, averaging, and also his works on the three-body problem. And well, just to have a personal memory about you, Ken. It's a very long time ago. I remember you dancing an evening in Mexico. Maybe do you remember? Well, anyway, I'm very happy to present your talk. So you changed your title. Your title now is something like 50 years around L4.
Something like that.
Okay, so please
point your telescope up there. I'm orbiting it.
Okay, so Annette asked me to ask everybody to close your microphone and camera so that the connection be better. So see you at the end of the lecture.
I have to know what I'm doing first.
You have to click in presentation, and that's
entire screen.
Yeah.
Wow.
It's coming. It's okay. We can see your full screen.
Okay.
Now you're supposed to choose the PDF.
There we go. Everybody sees it?
Yes.
Yes.
See. Yes.
Hildeberto, welcome to the Over 80 group. As a fellow octogenarian, welcome. I want to do a little bit of background on my work and then talk about some recent work I finished with Dieter Schmidt. So I'm going to talk about all the things about that I did relative to L4. So, way back in my college days, I met a fellow, Julian Palmore. We were students together. He got his PhD, I got my PhD in the Lyapunov theory, the old-fashioned Cottington, Levinson, Hale type of differential equation. Julian got his PhD in celestial mechanics under André Dupré. So years later, we met again at the University of Minnesota in 1970. He had programs on his computer, and I'm not talking about a little laptop computer, I'm talking about a big mainframe, and he was computing periodic orbits. This mainframe was used all the time, so you do all your computations at night, like 3 o'clock in the morning. He had all these periodic solutions, and he came in one day and he said, and this whole family of solutions collapses into L4 as mu, which is mu1. And I realized that's a bifurcation problem. I said I could prove that. So after many, many failed attempts, we sort of proved it, almost. And the results followed from that encounter for the next 50 years, or plus or minus. The first one was a paper with Julian, Bridges of Periodic Solutions in the Restricted Problem. Then Dieter Schmidt and I did Hamiltonian-Hopf bifurcation. We did 2 stability problems at L4. L4 is stable at a critical value. They computed this Km determinant, and it was 0 at one point. So Schmidt and I calculated a lot more and extended the theorem so that we could prove it was stable even at that critical value. More recently, we we proved the stability at mu1. That was sort of unexpected. And then we did what I'm going to talk about basically today is an evolution of the invariant manifolds at L4. And with 2 papers, I did one with McSwiggan, and it was sort of almost impossible to understand. So Dieter Schmidt and I got a much better result, and it's almost understandable. That's a recent thing. So that's what I'm going to talk about today, the recent result by Dieter Schmidt and I. So recalling things, restricted t-Brada problem is the problem with 2 finite masses, M1 and M2, rotating around a circular orbit, and in a coordinate system that's fixed. So it's a coordinate system that fixes the 2 masses on the x1 axis. So it's a rotating coordinate system. There are 5 equilibrium points, traditionally denoted by L. It's for Lagrange, and the one I wanted to is the triangular point, L4. L5 and L4 are essentially the same. So there's a parameter mu, which is basically the ratio of the masses M1 and M2, and we're going to look at the linearization of the equilibrium point for a while. First of all, the eigenvalues for small values, mu less than mu1, a certain critical value, the eigenvalues have the eigenvalues are pure imaginary. And for the other, for mu1 up to a half, the eigenvalues are real, have real parts. So what's really new about the talk today is something I learned recently is, what does a neighborhood of this critical point really look like? If you're looking at old standard differential equations, x dot equals f of x in Rn, a neighborhood of an equilibrium point is just a ball. We understand that. And you can isolate it by putting spheres around it. That's the basis of Lyapunov theory. That's what I did in my first 10 years, basically. Lyapunov theory and things of that ilk. But when you're doing a Hamiltonian system, you want to look at the flow in an energy level. So you want to look at what's near L4 in an energy level, but the problem is the Hamiltonian is critical at that point. So you can't say, oh, it's a 3-manifold. So what does a neighborhood look like? A neighborhood looks like a suspension of a 2 torus over a point. Well, you can sort of try and understand that. But another way of looking at it, it's a solid torus, 3 torus, with the center identified to a point, the equilibrium. Now, I've tried to think about that. It's hard to think about because it's, you're not in Rn, you're not in R3 anymore. So anyway, it looks like a solid torus with the center a point. And so you'd isolate the center by 2-dimensional tori surrounding the equilibrium point. So that's the basis of KM theory et al. So here's a picture. The coordinates mu1, mu2, and so on come from another paper, so you don't have to worry about that. The level looks like a solid torus, that sort of pink circle you see here, with the center circle, the blue circle, identified to a point. So the neighborhood of the origin looks like the equilibrium of a solution. So you should also think invariant tori, cross sections, area-preserving maps, twist maps, KM theory, Birkhoff-Eckstein theory, etc. Well, I think I did almost every one of those things at L4 at one time or another. I talk about L4, but I'm really talking about that general mathematical equation. So Here's a summary of results that I was responsible for. At L4, there are periodic solutions. Excuse me. I'm trying to read my own thing. Just a summary. L4 has two families of periodic solutions when mu is from 0 to mu1. And beyond that, they have a stable and unstable manifold from mu1 up to 1/2. Our results finish up the stability question. Classical KM theory and the calculations of André Dupré prove that L4 is stable in almost the whole range from 0 to mu1, except for one value where a determinant is 0, and Dieter Schmidt and I calculated and got that to be non-zero. The classical Hamiltonian-Hopf treats the evolution of the periodic solutions. Today, I'll talk about the evolution of the stable and unstable manifold. As I said, this one is joint work with Dieter Schmidt. Okay, going back to the general problem, just look at an equation, Hamiltonian equation in R4, Hamiltonian H, with a parameter nu, and z equals 0, an equilibrium point for all values of the parameter. The equations of motion look like that, where A is the linearization of the equation about the origin. So A is a 4x4 Hamiltonian matrix. And we want to look at the case where A has eigenvalues, pure imaginary eigenvalues, and it's not diagonalizable. That's the generic case for this. So that's what A is. What one does today is, giving that kind of situation, you find the invariants for that problem, and the invariants are these four capital gammas, gamma 1 to gamma 4, where knowing what the invariants are, you can write down what the normal form for the equation is. So H is gamma 1, that gives you the diagonal part. Delta, gamma 2, that gives you the off-diagonal parts of the linear. And then the higher order terms only depend, after you've normalized the equation, on gamma 1 and gamma 3. Now delta is equal plus or minus 1, depending on the matrix A. So this is what, if you just look at gamma 1 plus delta gamma 2, you get this Hamiltonian system, and you see delta is the gives you the off-diagonal terms. The eigenvalues are plus or minus I. I must admit, always, I scale everything to get rid of as many parameters as possible. So here I'm going to scale the variables by epsilon. Epsilon is a small parameter. Doing some other fussing around with the equation. Excuse me. The Hamiltonian looks like gamma 1, what's the diagonal terms, then the correction terms, the epsilon terms. You have gamma 2, that's the off-diagonal term. Nu, gamma 3, that's the detuning variable. And then there's one higher order term, which is crucial to think, eta times gamma 3 squared. And that's the crucial nonlinear term that we're going to assume is not equal to 0. And I can scale it so it's either plus or minus 1. There are two cases depending on the sign of eta. Let's look for a second at the problem when epsilon equals 0. Once I've done all these square lines. So I'm going to look at just when epsilon, you just get gamma 1. recalling what the gamma 1 was, it's these variables. And on the integral manifold, gamma 1 equals 0. In terms of the variables v1 and v2, u1 and u2, it's this bottom equation. u2 squared plus v2 squared equals u1 squared. You see that's an equation of a torus, actually, a 2 torus. But you let that vary from some finite value down to 0, you get a torus, a torus, a torus, and then when it equals to 0, you get a point. So I'm looking now at a neighborhood of the origin in this changed variable system. And that's how you get to this picture that I gave you earlier. The level set when gamma equals 0 is a solid torus with the center indicated by a blue circle identified to a point. So this is how you get to the topology of the neighborhood. The neighborhood of the origin looks like a neighborhood of a periodic solution. Okay, so that's the only new thing. Now you just pull out your old bag of tricks. Change variables many times and identify a cross-section in that torus and compute the section map. I won't bore you with all those details. I can send you a copy of the paper if you're interested in that, but it's standard material. So you get this is the approximate cross-section map. If you look at it carefully, you see that it looks like the time epsilon map for the Hamiltonian given below. Now that's a fairly simple one. You got a q squared and a minus p squared. Okay, that's looks like, depending on the sign, it either looks like a circle or a hyperbolic point. And then you have this, their higher order term, eta p to the fourth over 4. Now remember, this is the nonlinear problem variable, and we're assuming it has 2 values, plus or minus 1. We can scale it. You can't scale a sign away, but you can scale the size away. So given that, let's adjust things. We have 2 cases, 2 theorems, basically, lemma theorem, depending on the sign of this higher order term. Look at the picture. Remember, I'm looking at the cross-section map of here. The cross-section map in the torus is given by this complicated formula, but it looks like the time epsilon map of this L down below. So what I'm going to plot is what does the level lines of L look like here in low dimensions. So that's what plot on at the bottom. We're looking at the case where the nonlinear term eta is -1. And we're going to look at, we're not interested in periodic solutions today. We're interested in stable and unstable manifolds. So in these pictures below, the stable and unstable manifolds are indicated by red. Okay. On the right, where nu is positive, you have the stable and unstable manifolds just as curves tending to the origin. this would be the non-degenerate case. When eta equals 0, it's a degenerate case, and we still have something that looks like a stable and unstable manifold, but now there are curves that are tangent to each other that look sort of like parabolas. To this approximation, they are. Okay, so the origin still has a stable and unstable manifold, even at the critical value. And then moving to new negative on the left, you see that the stable and unstable manifolds are following in this picture a critical point, a hyperbolic critical point. Now remember, this is the approximation to the cross-section map in this complicated torus with the origin as the origin as a critical point, as the center circle. Okay, so from this you can get the theorem stated above. The stable and unstable manifold of the fixed point persists for negative values, that's the right side of the picture, and continue for eta positive. Have I got it backwards? No, I've got, it's just I keep saying it backwards. Anyway, what happens to the stable and unstable manifold is you go from the right in the pictures to the left. The stable and unstable manifold of the origin, they persist at the critical value as somewhat degenerate, and on the left of your picture, when eta is negative, they detach. Now, if you're talking about the cross-section map, it looks like a periodic solution. It looks like a critical point, but this is an approximation to the cross-section map, so that's a hyperbolic periodic solution. So the stable and unstable manifolds of the equilibrium detach from the origin and follow a hyperbolic periodic solution. Okay, now I've just drawn this as the cross-section of an approximation. You've got to realize that when you actually what you can prove are just the local theorem, and that's what's stated in the theorem above. You don't get all that structure that I showed. The structure that in the pictures are from the approximation. So that's what happens when when nu equals -1. Now that is not the restricted problem. Eta equal +1 would correspond to the restricted problem. So then you look at the pictures below. On the right side of the picture, eta nu positive, you have the stable and unstable manifolds exist, and they're connected. This is in the approximate equation. And as your unfolding parameter decreases to 0, that whole structure collapses into the origin and disappears at the critical value, nu equals 0, and it's gone. So the stable and unstable manifolds are globally connected for nu positive. And again, the pictures are the approximate equation. All you can show in the full nonlinear equation is the stable and unstable manifolds persist for nu positive, and you can show they intersect, but you don't know they're degenerate like this. They could be totally degenerate, as you see in this picture, or they could have transversal intersection. And of course, that's what you love, because then you've got all of Smale's theory of, going back to Poincaré, actually, Poincaré and Birkhoff and Smale, hyperbolic fixed point, generates all kinds of periodic solution. We can't show that. We can show that the stable and unstable manifolds exist and they intersect just by an area preserving diagram, but you can't take it all the way out to show whether they intersect exactly, identically, or they have a transversal intersection. We leave that up to the numerical analysts. So careful. These figures are all, yeah, I should have said that earlier. These are, you see in this picture, two on the right, two critical points, but that's a double cover. So they should really identify those as the same. There was this hidden thing I said, many changes of variables. One of the changes of variables used is a double cover. So in this picture and this picture, the right and left side represent the same thing. These figures are double covers of the actual section map, and you have to unwrap the figures. And I tried to actually draw them, and it's sort of impossible. And the other thing to be very careful of, only the local and stable and local unstable manifolds are found. We know they exist, and we can continue them to some extent, but we can't answer really fundamental questions we'd like to be able to answer, whether they intersect transversely or not. That's all I have. Thank you.
Thank you very much. So we have plenty of time for questions, comments. Yeah?
That's the advantage of being over 80. You can have a short talk.
Even before. So who has a question?
Okay. Is it
Yeah,
a
Jeff?
general phenomenon that when you have a bifurcation at, in this case, B1, is it general case that B1 will be stable? Not just for L4, in any this kind of Hamiltonian.
Genetically half the time. It depends on that higher order term, the eta term in these equations. If it's one sign, it's stable, which is what happens in the restricted problem. The other sign, it's unstable. So generically, it's one or the other.
No, okay. So at the limit point, in this case L4, it's stable, and
Yes.
So in general, that as a limit point, it should be stable too, right? Not just L4. Do you think so?
I'm not sure. When you move you're at the critical point. Things are going to change at that point.
Right, change after, but at the critical point, is it more likely to be stable as in your case, in this case, L4?
No, it's a 50-50. It's a flip of a coin. Depends on that one higher order term.
Oh, okay. Oh, all right. So it does depend.
There were two cases.
Right.
One case is stable, another case is unstable, and you can prove it in each case. It's stable or it's unstable.
Okay, you are the high. Okay, the high order terms that decides.
Take the differential equation x double dot plus or minus x cubed.
Okay. I see. Okay, that term.
Sort of plus or minus. Actually, that's all the work is to get it down to that equation, x double dot plus or minus x cubed.
To get that term.
That's what I said. You do all these changes of variables, you're only getting it down to that equation.
Okay. Yeah, I see. Right, that term. Thank you.
Yeah, please.
Yes?
I've got a question, Ken. Yeah, I've got a question about that. Now, the discussion you've given here is the planar case, right?
Yes.
You're talking about the planar restricted problem. Is there something similar happening for the spatial problem, or you don't know?
Well, I'll just pull it off the top of my head. The other direction is sort of a harmonic oscillator, the third direction.
Oh yeah.
And so, yeah, you could probably figure out what happens in that case. You aren't going to get invariant. Well, no, there's in this perpendicular direction, you don't have a twist term automatic.
Mm-hmm.
People have looked at it. I just don't know it offhand.
Right. Now, in the planar case, all of those stable and unstable manifolds then are two-dimensional objects, I guess, right? So they're
Yes,
two-dimensional things fitting sitting in the phase space, basically, which is four-dimensional, I guess. Right? So
it sits in H equals 0, the stable
right.
and unstable. So that it lives in that torus with the
circle. I see. Yeah. So they're two-dimensional manifolds sitting over that the periodic orbit, which you identified to a point. That's what it looks like, right? Okay.
It's hard to visualize.
It is hard to visualize.
It's not R3.
Yeah, it's not R3. Yeah, that's exactly right. Yeah, it's interesting. Well, I'm interested in the rotation of those manifolds, right? Of those stable and unstable manifolds. How individual solutions rotate in some symplectic way around the fixed point, right? I'd be if you have my address, send me a copy of that paper. I want to look at that carefully. Okay. Okay, man. Thank you.
It is a lot of changes of variables.
Yeah, that's okay. I can handle that.
So it should also be true that for elliptic restricted problem, the same phenomenon, right?
Yeah, that's right. I agree. Yep.
So your result should work for the elliptic case too.
You probably have to add another parameter.
Right, but that's elliptical, that direction.
Some of it would carry over. There's no doubt about that.
Right.
Just what I have not thought about.
Okay.
Give it to one of your students.
Approximation. Mm-hmm.
So, other questions?
I have a question.
Yeah.
I'm still working on the numerical computation of those manifolds. And I assume it's a standard problem, but I only found one package in MATLAB that does these kind of computations. Is there any other? Does anybody know whether programs of that nature are available, or do I have to do everything from scratch again?
Dieter, numerically, does these unstable manifolds goes to L1, L2, L3? Can you see these things actually crosses to L1, L2, L3?
I just want, in the vicinity, I want to see that the two intersect transversally.
Right. But
that's what I'm looking
globally?
For.
Now, what about globally? Because there's these unstable manifolds, because if it goes very far, actually, it shows quite complicated behavior for these restricted three-body problem. And I remember sometimes these things can go really far to various regions in the space.
Yeah, I've seen that too. There's some paper from Chinese that follow them. And also, Jacques Henrin had done some of those computations. But a very careful computation near the vicinity where they might to see whether they intersect transversely or not, that I have not been able to find.
Yeah, I see.
Other questions?
Okay, I remember Jerry Marsden did some computations. They tried to do use it for space exploration, that use these unstable manifolds to carry the spacecraft from one region to another region. And they started with L1, and that goes just everywhere, basically, the unstable manifold of L1. And for this case, is in L4, that when it gets to be unstable, probably it does similar. It has similar properties.
This is a problem for Rick. He looked at this kind of intersections.
Right.
I don't know the answer to that. If I'm the Rick you're talking about.
Yeah.
So some other comment or questions? No? So if not, maybe Annette can appear.
Yeah, I'm here.
Yeah.
Do you want audio with the video?
Well, I don't know if there are no other questions.
Okay. I'm going to put the video. Wait a minute, please. Okay, could you see?
Yeah. So
Sonhei que estava em Pernambuco. Fiquei maluco quando o frevo passou. Mas quando estava no melhor da festa, ora essa alguém me despertou. Quando acordei, ai ai, até chorei, ai ai, tudo mentira, ai ai, o que sonhei, agora vou brincar, um frevo eu vou dançar, um frevo eu vou cantar, só pra me consolar.
Very good.
Thank you. So I think we can thank again Ken for his presentation. A nice talk which showed that there are still global mysteries in the restricted three-body problem. Thank you again. You want to conclude, Annette, with the now you are on holidays?
Next week we have Carnival holidays, so we don't have talk. Okay, it's a virtual Carnival, but it's always very important for us in Recife, in Brazil. So we don't have a new, but the next speaker in February 23, it's Professor Alan Chancinet.
Okay, so thanks again, and see you next time. And have a nice Frevo session. And a nice carnival.